Everybody in this section has their exam back. I have a couple from the other section that aren't yet. Thought they were okay. I think the average was about a 3.5 out of 6. You guys, the density of 5s in this class were much higher than the other sections, so you can give yourselves a hand for that one. No 6s, unfortunately. In fact, there were no 6s at all. That's okay. I didn't really expect to give 6s. 5s are probably practically the best grade you can get on the exam. Some people were pretty close. There was usually like one little problem somewhere that kind of threw off everything. But I think most people got the gist. Yeah, it was a little trickier than in abstract, a little more abstract than I thought, I think, initially. But I thought that the results were pretty good. Any questions about the exam? Okay. So we've only got about 5 lectures left in the class. I'm a bit behind, but that's because we've been going into good detail. I want to finish up atoms today and kind of get us into a good position for molecules for the rest of the class. It seems like a long trudge to molecules, but it's important to understand atoms because when we make molecules, we're going to add atoms together. I mean, the approach that we're going to do to figure out the energy levels of molecules and the structures of molecules is to literally combine atoms together to make molecules. So understanding the orbital structure of atoms is really nice because it helps us understand how to construct molecules. And the way that we're going to construct molecules is just linearly what's called linear combination of atomic orbitals. We've got to combine atoms together, different distances, add their orbitals together to create new orbitals. What we call molecular orbitals. So let's talk a little more about atoms today. We'll get kind of into multi-electron atoms. Right? We'll talk about helium, sodium, things like that. And what I really want to get at is not really focusing on the details of these atoms. Rather, I want to talk about trends. And because what we learn about hydrogen can really be applied to just about everything. There are obviously complications. When you have many electrons, the electrons can interact with each other. And that affects their spectra and their energy levels. And it's a difficult thing to model. I mean, you can model it, but instead I would rather be interested in the trends that we get as we move across the periodic table. Right? As we know, the periodic table encoded in some sort of trends. Right? There are trends in the periodic table. There must be some consistency to the theory. Right? All atoms kind of follow these trends, electronegativity, and you name it. I want to talk about these trends from the perspective of orbitals and energy levels today. Right, to get a sense of the underlying basis of the periodic table. And spin-orbit coupling plays a major role. In fact, the spin of the electron ultimately defines, and that's what you're going to especially learn on the homework this week, that the spin of the electron really defines the periodic table. It's really the power. It's really the thing that really gives us the table that we know. So let's look a little more carefully at spin-orbit today and then start to think about how spin-orbit coupling affects the hydrogen energy levels. We'll do that just for a little bit. We'll look at another example with sodium, and that'll motivate us to start thinking about trends. And how do we correlate atomic atoms to each other, and how can we use hydrogen to learn something about other atoms? So let's just recap again about this idea of spin-orbit coupling. We put our system on a 3-dimensional axis system, like we always do. All right, and this is gonna be our vector space. So it's not really a physical axis system, but rather an axis system for angular minimum. And I'm gonna label them as the projections of the angular minimum, the total angular minimum of the system along the 3 axes. All right, remember, J is the total angular minimum. Right, our coupling is that J is equal to the angular minimum L plus the spin of the electron S. Okay, and S, of course, always has a fixed length. Right, the length of S is always, hold on a second, H bar square root of SS plus 1. And S, of course, for the electron is 1/2, so that's 1/2 plus 3 times 3/2, 3/4. That's square root of 3 over 2 h bar. Sorry, yeah. Right, so that vector always has the same length, but L, of course, depends on the angular minimum. L plus 1. Right, L can be any value. Remember, L can be any value between 0 and n minus 1. Right, so the relative contribution of L and S depends on the level that you're in. Right, if your electron is spinning very, very fast around the atom, right, L is very large, then S doesn't really contribute that much, because S's length, if you add the vectors, is only square root of 3 over 2. Right, but what if L is like 5, right, or 4 or 5, right, and the length of the vector is, let's say 4 times 5 is the square root of 20 h bar. Right, so L is a very, very long vector, and then when you add spin to it, which only has length roughly 1/2, it doesn't really change the direction of the net vector very much. Right? So if I draw my vectors in that direction, so for instance, let's say L is pointing in this direction. Right, this is my L vector. Right, and then we have S being added to it, tip to tail, along this direction. Right, that maybe this is the plus half. Right, the net vector of precession for J is going to be along this axis instead. It decided not to give me the right direction. Right, it's along this axis instead. Right, remember that we only know one direction. Right, we only know one projection. We only know it along Z. Right, and that's true here too. But we can define J sub Z exactly. Oh, sorry about that. Turn my phone off. But we don't know anything about its position along X and Y. Right, so in fact, the way that we typically draw these vectors is not as a vector, but as a cone on the xy plane. So we could, for instance, draw, right, this vector J actually subtends a cone around the xy plane, right, and it can be along any of these directions. And of course, L as well has that similar property as well, and so does S. Right, S also, let's see if I can draw it. S also precesses around its axis, and L also precesses around its axis. All right, so you have these vectors that, and this vector, you have these angular minimum. We represent them as vectors, is that they're sweeping around these cones. Right, so this tells you something about the kind of the precession of the electron around the proton. Right, its orbit, whether it orbits here. The idea is that the electron's pointing in this direction. The electron is kind of orbiting, kind of in a wide cone around the z-axis, in this case. And S is in the same direction as the rotation. It adds to the angular momenta, right? That gives basically the spin is giving the orbit a little push in the right direction. And so your net vector is going to be even more towards the z-axis and precessing more like a top around the z-axis than it would otherwise, because the spin is giving it a little torque. It's giving it a little push. Okay, but there's also an equivalent result where spin can act in the opposite direction. Right, this would be S. Let me just say that this is S such that S sub Z is 1/2 h bar. Right, this is the positive spin, right, the counterclockwise rotation of the spin. But there's also an equivalent way to add well, not equivalent, but an additional way to add the angular momenta along this axis, where again, if L is in this direction, but spin is negative 1/2, meaning that it's rotating clockwise, not counterclockwise about the electron's axis. S would be pointing in this direction. And therefore, J you get a torque in the opposite direction away from the z-axis. All right, so J sub z here, the value of J sub z is going to be smaller in this case because the system is now processing closer to the xy plane than it was before. Right? The spin applies an opposite torque, a torque that affects the angular momentum in a destructive way, slowing the electron down. Right? It provides a braking force. It causes the electron to, instead of processing perfectly around the z-axis like the Earth does, more like a top, right, or a gyroscope. Right? More a wide rotation. Right? And the way that we would write this, again, that J here, if L is, let's say if L is equal to 1, then J is L plus S. That's 1 plus 1/2, which is 3/2. Right? So we have a total angular momentum of 3/2 greater than the orbital angular momentum because the spin is applying a positive supporting torque to the angular momentum. And here we have J equals L plus S again, but instead we have L plus minus 1/2. Right? And so if L is 1, then J is 1/2. Okay? So they had two different distinct orbits, effectively, for the electron, given a fixed value for L. Okay? Spin can either work with the electron or work against it. Now, I haven't specified what's more stable. Right? We haven't considered the energies of these. And how much different are they in terms of energy? Right? I've identified that they have there's two different angular momentum states that are distinct for this system. They should have different energies. The question is which one's more stable than the other? Right? How do they split? Or are they the same energy? Well, the answer is, of course, they are different energies. Because what's happened here is, again, it's a bit like having a magnet. Say your L is your magnetic vector for your dipole of your magnet, and you put it in a magnetic field. This is what you do in NMR. Put it in a magnetic field, and there's going to be an orientation where the magnet is aligned with the magnetic field, right, which is stable and low energy, and then there's an opposite orientation where it's anti-aligned with the magnetic field, and you have higher energy. Okay? You do that with charges in an electric field as well. Right, so there's going to be some preference to align or anti-align the spin with the angular momentum. And it turns out it depends on the atom, whether one's more stable or the other. We'll actually come up with a rule for it. But in general, one of them is going to be more stable than the other. So let's look a little bit at that. So I won't go through the quantum mechanics too much, but what you can show is that the energy of the spin orbit splitting of a spin orbit state, so the spin orbit energy of a height of a level, is a function of L, S, and J. Takes in three numbers. And it's equal to 1/2 times hc times this constant A squiggle, okay, which is called the spin orbit coupling constant. This gives you units of, just as FYI, this gives you units of joules. All right, and an A squiggle, the spin orbit coupling constant, is in units of wave numbers. Okay, so that's why hc is in there. You can always get rid of hc, and then everything's in units of wave numbers.
And is that just like an A with like?
Yeah, it's just a number.
Oh, okay.
All right, it's just a number. It depends on, as we'll see, it depends on a number of things. And this is multiplied by j plus 1 minus l plus 1 minus s plus 1. Okay, so given a value of S, given a value of L, and given a value of J, you can calculate the energy of a given level. Given it's J, it's S, and it's L. Now this is additional to the energy with respect to N. So the total energy of the state, so the total energy of an electron state is going to be the Rydberg constant minus R sub h over n squared plus the spin orbit coupling, ELSJ. Right, so what this means is that the energy is a function of n, right? You determine whether you're 1s, 2s, 1, 2, 3, 4, 5. And then there's an additional splitting depending on your spin orbit, right? Your angular momentum, right? So it's a small correction. Right? So the energies are actually formally dependent on all the parameters, right? L and J and N, right? All the angular momentum in our system. But of course the question is that the energies with respect to N are dependent on R sub h. Remember, R sub h is a very, very large number. R sub h, the Rydberg constant. Well, I'm not going to write equals. I'm just going to write equals because it is equals to it. It is equal to, let me just write it down one more time for you. It's about 100,000 wave numbers. Of course I can't find it. I have it up on my computer. Sorry, just a sec. Ah, here we go. Yeah. So it's Rydberg constant's 109,678 wave numbers. All right. So the difference between two energy levels in N is on the order of this number, right? Thousands and thousands of wave numbers. So the question, of course, is what's this energy difference at, right? What is the A constant, the size of it? Because the difference between N equals 1 and N equals 2, that's on the order of a fourth of the Rydberg constant, give or take, 3/4 of it. Right? That's a big number. That's like 80,000 wave numbers or something like that. Right? But so what's the difference then once you get to N equals 2? What's the difference between the different spin orbit states, right? Which was determined by A. Right? A determines based on L and J how much the energy changes. So if you do a little bit more analysis, you can actually come up with a nice little approximative formula for A, the spin orbit coupling constant. If I can find it. Notes. Yeah, here it goes. Right, and what you find, a little bit of math, is that A is equal to z to the fourth. Z is the charge of the nucleus. Right, so I'll write that down here. So for hydrogen, it's 1. Helium, it's 2. Right? So it scales as z to the fourth. And then there's this number mu naught over 4 pi. This is what's called the magnetic constant. It's just a number. I'll put all these together into a final constant in just a second. This is called the magnetic constant. It tells you how much magnetic field a single electron generates. It's a bit like the epsilon naught for the electric field, right? It tells you how much charge you can store in a meter of empty space. Mu naught tells you how much magnetic strength, how much magnetic flux, that magnetic field you can store in a meter of empty space. So it's the same idea. And then it's times this number called G. G sub J. This is G sub J is called the lambda G factor. And for hydrogen, or for the electron, for the bare electron, G is 2. It's just 2. It's just the number 2. roughly. That's roughly 2. It's actually a little smaller than that, but it's roughly 2. We'll see that on the homework, you'll see that number varies. And then it's multiplied by one more constant called mu sub b squared. Right? Mu sub b is called the Bohr magneton. This is the magnetic dipole moment of the electron. All right, so it tells you how strong of a magnet the proton-electron system is. All right, it's a fixed number. It's a constant. It's called the Bohr magneton. All right, and then it's times this big fraction. That's a function of the quantum numbers. First, it's it has a scaling factor, a Bohr radius to the third. And let me do it in a different color, sorry. I want to do this explicitly. It goes as 1 over n cubed, where n is the principal quantum number. L plus 1/2, L plus 1. Okay, so again, this is just a lot of numbers, all right, and I'll simplify it for hydrogen in just a second. But let's look at the scaling here. Okay, so what this says is, again, this number measures how much two different angular minimum spin orbit states for a given orbital split. The splitting is dependent on 1/2 this number, roughly, proportional to it. So how does it scale? Well, it says that the bigger the atom is, as you go down the periodic table, the coupling increases as z to the 4th. Okay, so all things being equal, the coupling when you go from hydrogen to helium is 2 to the 4th larger. That's 2, 4, 8, 16 times larger. Okay, so if we'll look at that in a second. If you look at the helium 2p orbitals spin orbit, the p3 halves and the p1/2 state for the 2p orbital of helium, that splitting is about 16 times the size it is for 16 times the size that it is for hydrogen. And so you can imagine that when you start to get to atoms that are down the periodic table, right, you get into the D block and you get into the F block and the lanthanides and the actinides, the coupling of the spin orbit coupling is so large that it can start competing with the main part of the orbital energy. Right? This significantly will complicate the spectra of these atoms, and I'll show you a picture of that. All right, so the splitting will just get larger and larger and larger as z to the 4th. All right, but it also gets smaller by some numbers. Right, it scales as n cubed. So when you get down into the D block, into the F block, right, the valence electrons in those atoms are in the 4 and the 5s, you know, the 4Fs and 4Ds and 5Fs. There you're going to get a reduction in the spin orbit coupling because n is large for that valence, but it doesn't really compensate for the z, right? Z to the 4th will grow much faster than n cubed, right? Because n cubed really only changes as you go down a row, right? As you go down by octet, if you will, right? Per valence orbital. So this really only changes on average in the valence per row, but this obviously moves a lot across a row. And then again, the spin orbit coupling becomes smaller if you have more orbital angular momentum, right? And that should make sense because, let's just go back to our vector picture for just a minute, that the net angular momentum that we see for the electron is the sum of the two vectors, L and S. S is the same length regardless, right? Because the electron always is spin 1/2. So you're always adding either a plus 1/2 or a minus 1/2 spin vector to L. So when L gets really long, like you're in an F orbital and L is 3 or 4, right? The length of that vector for 4 is 4 times 5 square root of 20 compared to the square root of 3 over 2, right? Where this number is just above 1. Right? So the length of the spin is about 1, but the length of L is on the order of square root of 20. It's 5 or 6 times longer. So when you add a vector that's 6 times shorter to L, it doesn't really change the direction of L very much. Okay, so that means that when you add spin, the angular momentum, orbital angular momentum only shifts a little bit between the two states, two spin orbit states. And so the energy doesn't change that much, right? Because the angular momentum is not changing much. So it's dependent on the length of L. Okay, and then I give you these numbers. So the rest of these numbers, this will actually do a problem on this on the homework. I give you all these constants, okay? So you don't have to worry about it too much. And so for hydrogen, let me just simplify this for hydrogen. For H atom, A is 1.1608 times 10 to the minus 22 joules over n cubed L plus 1/2 L plus 1. So I've just accumulated all of these little constants together and just put it in units of joules, as it should be. It should be in units of joules.
Is that times 10 to the negative
22.
Oh, okay.
22, yes. It's just under all right, it's just about a joule per mole. It's about a joule per mole. Not a lot of energy, right? Not a lot of energy. Given the fact, right, so let's just do a quick calculation. So let's look at hydrogen's p states, the two p states. So the energy, so let's just do it, let me just write here, example. The energy of the 2p, so let me write it like this. This is the n equals 2. So that's the 2p 3/2 state. And this is from NIST, is 82,259.28 wave numbers, 285 wave numbers. All right, so that's the state where this L equals 1, right? The P angular momentum adds constructively with the spin, right? The 3/2 state. And then the 1/2 state, the one where they add differently, or they subtract off each other, is equal to 82,258.919 wave numbers. All right, the splitting's not very different, right? They're pretty close together. Delta E here between these is 0.3659, let's say 366 wave numbers. All right, which is a very, very small amount of energy. I'll give you a version in kilojoules per mole. So I will tell you this is about, for me, I'm a frequency guy, so this is about 10 gigahertz in frequency. And in energy, it is, I'll give it to you in just a second, a very small amount of energy. Yeah, it's 4.3 joules per mole.
For the E22P sub 1/2, is that 8?
2258.9. 8228, sorry. 82258.919. Yeah. 4.3 joules per mole. So they changed by a very, very small amount, okay? So we can calculate, so let's take this number and calculate the spin-orbit coupling constant for hydrogen, or for this state. Right? What is the actual number for A in this situation? And let me see, I need page 51 here. Excellent. Okay, so let me go to the next page. So we have delta E between those two states is 0.366 wave numbers. All right, and this is going to be equal to the energy, the spin orbit energy, so I'll call that SO, of the 3/2 state minus the spin orbit energy of the 1/2 state. Okay, and so we just plug in our formula. So let's just remember what our spin, so for the spin orbit energy we need L, S, and J. So L here is 1, S is plus or minus 1/2. And J is either 3/2 or 1/2, depending on which spin we choose. Okay, so all we need to do is plug that into that formula I wrote before. So we'll do E 3/2 is going to be 1/2 A. I got rid of the HC because we're doing things in wave numbers. We don't need H times C. And this number comes out to, first we put in J. It's J plus 1 minus L plus 1 minus S plus 1. So we have 3/2 plus 1. Now we do L plus 1. That's 1 times 1 plus 1. And now we do S. That's 1/2 plus 1. And sorry, I forget. I apologize. Its spin is only 1/2 here. A plus or minus 1/2 is the projection on the z-axis. We don't. Sorry, there's no negative sign here. It's just plus 1/2. S is positive. All right, so that's our energy for that state. And we'll just quickly write it down for the 1/2 state. This is going to be 1/2 A. And now we just change the J to 1/2. L is still the same. And spin is still the same. Okay, and so now the energy difference between these two are going to be the difference of these two formulae. So delta E is equal to E 3/2 minus E 1/2. All right, so as you can see, a lot of things cancel out. All right, we got to subtract this from this. So the S part cancels out, it's the same, and the L part cancels out. Right, the only thing that's different is the J value. So we're left with 1/2 A on the outside. And then the difference of the two J terms. Okay, so let's calculate them and then we'll just subtract the difference. So 3/2 plus 1 is 5/2. 5/2 times 3/2 is 15/4. Is that right? 1/2? Maybe I calculated that wrong. 3/2 plus 1, that's 5/2. Yeah. So this is, so we have 3/2. So 3/2 plus 1 is 5/2. 3/2 times 5/2 is 15/4. And then we subtract from that 1/2 times 1/2. The 1/2 plus 1 is 3/2. 3/2 times 1/2 is 3/4. I think my numbers are wrong here. Hold on a second. So what does this work out to? Oh yeah, no, this is right. This is right. So this is 1/2 A times 12/4.
And you said we're getting rid of the 1 plus 1 because they cancel out?
Yeah, they all cancel out.
Okay.
So the net result is that the energy difference is equal to 3/2 A. Okay? Yeah, so again, subtracting this from this, they go away. This from this, it goes away. So we're just left with the difference of these two terms right here, which is 12/4, which is 3. 3 times 1/2 is 3/2. So the energy splitting between the two P states is 3/2 alpha, or A, if you want to call it. Right? So we know what that is. We know what the energy difference is. It's 0.366. So that means that, therefore, delta E, which is 0.366 wave numbers, is 3/2 A. Okay, and that implies now here that A is 0.2439 wave numbers roughly for hydrogen. Okay, it's not a big correction. Not a big correction, right? Given that the fact that the energy levels, remember, they're at 80,000 wave numbers, right? So you've got two lines at 80,000 wave numbers roughly that are split by 2/10 of a wave number, right? It's very, very narrow splitting. But think about now for helium. Helium has 2p states as well, 2p3 halves and 2p1 half, just like hydrogen does. But its state is 16 times greater, right? So the coupling constant for helium for these two levels, the spacing between the helium levels, is 16 times this number, which again is still not a big number, right? It's about 3.5 wave numbers, right? 3 or 4 wave numbers. But you can imagine how quickly this scales, right? Once you go to lithium, now you're at 3 to the 4th. I can't even do that. That's 9 times 3, 27 times 3, which is, I don't know, 80 something, right? 80 times bigger. And then you go to, what's after lithium? Beryllium. Right? You get an extra, it's 5 to the 4th. Then you get by the time you get the carbon or boron, these are huge. And so spin-orbit coupling scales very, very rapidly across the group, or across a row of the periodic table, and it causes the levels to split dramatically. Right? So let's look just kind of roughly at that. So in the hydrogen, so the Lyman alpha transition for hydrogen, which Lyman saw old school assignment, is n equals 2 to n equals 1 emission, or an absorption would be the other way around. Right? And that's, of course, going to be at some energy. The energy of this transition is going to be at the Rydberg times 1 minus 1/2, right, which is 1/2 Rydberg. Did I get that wrong? No, sorry, 1/4. Sorry, 1/4. It's n squared, so 1/4. So that's 3/4 Rydberg. And Rydberg is about 100,000 wave numbers, so this is kind of around 80,000, around 78,000, 78, I forget exactly. Let's say 80,000, roughly 80,000 wave numbers. Right, that's what we saw. Right? Pretty good prediction, right? So this is what Lyman sees. He just sees one line and it's 2 to 1, right? But we have a more intricate way to measure this now. Right? So we have the 1s state here at some energy level. All right, and then there's the 2s up here. But remember, the 2p orbitals are in the same energy level. They're degenerate with the 2s. They're at the same energy. Right? So all the 2p's are right here as well. Right? And Lyman says my transition is this. This would be a singlet from the 2 to 1, and it's at 3/4 of the Rydberg.
Is that 100,000 wave numbers for 3/4 of?
No, it's closer. It's 80,000.
Oh, okay.
80,000. The actual number, I'll tell you exactly what it is. I wrote it down on the previous page. Basically, it's the difference of the two frequencies of the two spin orbit states. Which I've lost my page. I have too many pages today. Here it is. Yeah, sorry. It's roughly, I'll just say it's closer to 82 to 59 wave numbers. All right, so this is at 82,259 wave numbers. All right, so that's what Lyman sees, but we know that these lines are actually split a little bit. And these lines split into a doublet. So first of all, the S state gives me a 2s 1/2 state, and you can show that that lowers the energy of it. Once you use that formula that I used above, it actually brings the energy down a bit for the 2s 1/2 state. And what you find again is that the 2p 1/2 state is lower in energy. It's also the lowest energy state because, again, the formula for the spin orbit energy is proportional to jj plus 1. So the smaller the j, the smaller the energy. And then it also, there's an additional state now here, which is the 2p 3/2. And the spacing between these energy levels is 0.366 wave numbers. So the energy that what we actually observe are two transitions. We observe this one, and we observe this one. Right? This is our Lyman alpha doublet, our spin orbit doublet. Right, so the Lyman alpha line, the fundamental transition of the hydrogen atom, as I would like to call it, is actually a doublet, and it interacts three different lines. The S spin orbit state for the ground state. Right, there's no L there, so S and J is 1/2. Only one state for S, and then there's a doublet for P, 3/2 and 1/2, and they scale as the energy, or as the J. Okay, so this actually explains that doublet that they saw in the 1920s. Okay, you may find that it's very interesting that there are notice that there's also an S state in here as well. But the S state has the same energy, as far as we can tell, as the P 1/2 state, right? Because let's go back and look at the energy again for this. Remember, the spin orbit energy depends on J. It depends on L. Sorry, it depends on J, and it depends on the difference in L, the difference in J, and the difference in S, right? The difference in L between this state and the S state is not changed. And the J's are the same between the P 1/2 and the J 1/2, and the S 1/2. They both have the same spin and the same J. So in fact, there is additional level in here hiding at the same energy, roughly the same energy, which is the other 2s 1/2 state. Right? It's hiding in there. There's another state in there, right? Because you have to account for the S orbital. But the S orbital has the same J as the 2p 1/2. They're both J 1/2. They have basically the same energy. It turns out they don't have the same energy. They have a slight difference between the two. This was not discovered until the 1940s. So informally in our case, the energy difference between the n equals 2s 1/2 state and the n equals 2p 1/2 state is 0. But it turns out that they measured it. Let me find it one more time. I will find the exact number. But there was a man, let me find his name, Lamb. What's his first name? There's something called the Lamb effect, which is a very, very, very small effect that actually splits these two levels, and it's due to relativity. The fact that the electron is just moving at this very slight fraction of relativistic speed, and actually so is the proton is orbiting itself, it has a little angular spin angular minimum as well, and it's slightly relativistic, causes a slight difference in the energy between these two. And the energy actually between these two states is on the order of 0.003 wave numbers. It's about 1 gigahertz. All right, so you need a microwave photon to be able to measure it. Right? And this was discovered in the 1940s or 50s. Right? It's a very, very tiny effect, the Lamb effect. Right? So these levels are actually split right here by a very, very tiny, right, 1,000 time effect that's 1,000 times smaller than spin orbit. Okay, so there are actually 4 states in the Lyman alpha transition, but we only see 3 of them. We only see interactions between the ground state and the 2p states. The S state is invisible. Now, why is it invisible? Well, we haven't considered what transitions are allowed in the atom, right? Remember, and you've learned this in the midterm, that with vibrations, only certain transitions are allowed, right? The overtone in vibrations is very weak compared to the fundamental. Atoms have similar rules as well. So the only transitions that we see when we do Lyman alpha is the S to P transition, right? We see a doublet. We don't see a triplet. We don't see any S to S intensity at all. It's a very weak transition. In fact, the way that people discovered the Lamb dip is not by finding transitions from this S state to this S state. We'll see that that's not allowed. But rather by finding transitions between the S and the P state at 100 megahertz, right? They actually probe this splitting and find an absorption. And that's where it was discovered. So why don't we see a triplet here for the Lyman alpha? Or rather a very, very closely spaced doublet and then another line that's a little further away. Why is it not a triplet? So you may be able to rationalize this a little bit. Is that when I have the intensity of a transition, again, has to do with an integral of the wave function of the lower state times the wave function of the upper state times the dipole. Right? And the dipole, as you know, is an odd function. It's roughly a distance, it's function of the distance. And so in order for the intensity to be non-zero, the product of the wave functions has to be odd overall. So that when you take the 2 wave functions that are odd overall and multiply them by an odd dipole, you get an even function and the integral survives. All right, so it's the same idea as vibrations. Right? 0 to 2 is formally forbidden in vibrations because 0 and 2 are both even functions and the dipole is odd, so the whole integral is odd overall, therefore it integrates to 0. Everything needs to be even symmetry. So an S to S transition is always forbidden because you're going from a spherical state that's even to a spherical state that's even using a dipole operator that's odd. So you have an even function times an odd function times an even function. It's odd overall. So when you integrate overall space, the integral cancels out. So S to S transitions are formally forbidden. There's actually a name for this. So let's talk about that. These are the selection rules for atoms. Right? How do we, using light, right? What transitions are allowed with light? What are light? Light allowed transitions for atoms. Okay. And the rules are very, very simple. All right, so what I've claimed is that you can't move from S to S. So there's a very simple rule that's actually very, very hard. And the first one is probably the one is that delta L can either be 0 or plus or minus 1. But for hydrogen, only delta L equals plus or minus 1 is allowed. This means that S to S is forbidden, but S to P is allowed. Okay, so you can take an S electron and put it in a p orbital, or vice versa, but you can't put an S and put it in another S state. Right? That's why the S states in the alignment alpha, the excited S state, the 2s state, is completely invisible. There's no absorption to it because it's not allowed. This also means that you can't take an S electron and put it in a d orbital, because that would be delta L equals 2. And I'll write that too. S to D is forbidden because delta L is equal to 2 here. Okay? So the only way that you can excite electrons in an atom, basically, is by taking an S electron, put it in a P. If you want to get a D, you got to take it in a P and then put it in a D. If you want to get an F, it has to go D to F. Okay, so it has to go in a chain. You can't just take an S orbital, an S electron, put in an F orbital. Right? You have to use multiple photons to pump it up. Right? You can't just freely go wherever it wants. Okay? And then one of the hardest rules in all of chemistry, very few things break this. There are exceptions, as there always are in chemistry, but this is a very good rule for anything, is that the spin of an electron can never change. All right? So you can't take an up electron and flip it down across the transition with light. With light, that's the important thing, with light. Electron is always, its spin is always conserved. Okay, so if you have a spin up electron in an orbital and you put it into another orbital, it's always going to be spin up. Right? In multi-electron atoms, this has a lot of consequences because I'll give you an example. Right? So in hydrogen, it doesn't really matter because there's only one electron. Right? But what if you had something like this? Right? What if you had an electron configuration that looked like this? Right? We've got two P's. Let's put a 1s, 1s, 2s, 2s. And we'll do it like this. Okay? And let's think about what are the excitations that we can do between these levels. Well, so I could, for instance, take this electron, right? If I take this electron and excite it, right, it can go to any of the three states, right? These are all allowed, right? Because the spin down electron can go into this orbital, obviously it can go into this one, they're the same. And it could go into this one because there's none in there, right? There's three possible transitions. But what about for the up electron, right? What about the other one? Well, that one can only go here, right? It can only go there because it can't go into these because they already have spin up electrons in them, all right? So you can't do any spin flips. You also couldn't take this electron or this electron and just flip it without changing it. Okay, so there's no way to just flip a spin with light. With light, that's the important thing, with light. All right, this is a really hard rule. This is true for molecules too, right? In fact, the reason why glow sticks glow for as long as they do is entirely dependent on the fact that delta S is equal to 0. I know that sounds crazy, but the idea is that in a So let me show you, let me just give you an example about this. So in glow sticks are a 3-level effect. They have a 3-level effect in a glow stick. So imagine you have 3 levels here that look like this. Let me make them a little more dramatic, but just different energies. All right, this is your ground state. So we'll call this 0, 1, and 1 prime. right? They're not labels of anything, they're just generic labels. And a glow stick will have an energy level like this. And so there are some special rules, okay? Let's say, for instance, that this state down here corresponds to a molecule of paired spins in the valence. And this one also accounts for paired spins. But this state right here is actually two different orbitals. Let me do it like this. There's two orbitals. One's empty and one's full.
Is that one prime over there?
Yeah.
All right.
Right, and maybe this state over here represents two unpaired electrons in two different orbitals. Okay, so we have a full set here with an empty pair, and then one over here where they're half. All right, and so what happens with the glow stick? Okay, so you apply some mechanical energy to it, right? You break it. And what does that cause? Well, the mechanical energy imparts an energy to excite the molecule from the ground state to the excited state. Right, this is the breaking effect. Okay, and the molecule can easily just come back down and emit a photon at the same frequency or wavelength as this light really quickly. Right, it can also do that.
And what is the next to the green arrow? Photon?
Breaking.
Oh, okay.
Yeah, breaking or cracking the.
Yeah.
You know what I'm talking about?
Yeah, I know.
Right? It can also decay rapidly and just go backwards as well, right? Which is do nothing. Right? This is typically an ultraviolet transition, so you don't see the light from this. It's a very fast, you break it, and there's a possibility it gets up into this excited state. This is UV. So we'll say this is ultraviolet. Okay, and it gets up in this state, and it can easily just come right back down. It's perfectly allowed, nothing wrong. All right, but it would just emit a photon, and it would just decay immediately. You wouldn't have a glow stick. You just excite it, and it goes down. All right, but there's a possibility, right? There's a possibility that, a very, very small possibility, that you get a spin flip like this. So even though this is formally forbidden, there could be, if the spacing between these two levels is close enough, so the energy difference is delta E, and delta E is close to 0, all right, so if these energy levels are really, really close together where you have two states where the spins are flipped, one of the spins are flipped, but if the energy is close enough, there's a possibility these two states will mix, and there's some probability that the electron the state will fall into here. All right, so what happens is that very slowly your excited state population will get siphoned into this intermediate state. Right, this is slow. Right, and now the molecules, so you can imagine this, all right, so ignore them coming down, that's just going backwards, it's doing nothing. It's just, this is the undo step. Right, so it breaks, and then there's a very small probability, maybe 1 out of 1,000,000 molecules in your glow stick will fall into this level, this intermediate level over here by flipping a spin. Okay, very, very, very unlikely, because delta S equals 0 is very, very strong rule, but it can be broken, and it is broken, but it's very, very rare. So the process, the kinetics of going from here to here are very slow, right? For every 1,000,000 molecules that come up here, maybe only 100 end up in here. Okay, so now the molecules are in this weird intermediate state. They obviously want to relax down to the ground state eventually. They want to get rid of their energy. But they can't, because this level, this state right here.
Dr. Seifert,
yes, sir.
The green arrow where it says
slow.
Oh, okay.
Slow. It's a slow rate. Yeah, so ideally what they want to do is get back into this state, right? We start all over again. I think that's always what molecules want to do. They want to be lazy and lowest energy possible. So when the molecules get trapped in this intermediate state, they have to find some way to get down here. To the ground state, but there's no real easy way to do that, right? Because this transition requires a spin flip. Right, so this is delta S equals 1. And the energy difference between these states is very, very large. This state's way down there. All right? And when two states are really far apart in energy and they don't have good overlap, right, the integral between them is 0, which is what this implies. It's forbidden. The probability of a molecule coming from, or an atom going from here to here is extremely rare. It happens very, very infrequently. Very rare. But eventually it does happen. It has to eventually at some tiny, right? This is a very slow relaxation. But every once in a while, a molecule trapped in here will relax and emit a photon. Right? It'll relax and go into the ground state and emit a photon at this energy difference. And for a glow stick, this energy difference is green. Right? This is a visible photon. So emits a photon, a green photon. Right? So what you're doing is you're exciting your molecules and then slowly siphoning them into this trapped state, this intermediate state where they get trapped. That's lower in energy than the original excited state. Okay? Remember, this is UV. We don't see any of that. So we put it in an intermediate state that's slightly lower in energy so that when these molecules get out of the trap and fall back in the ground state, they emit a photon at this energy difference, which is in the visible. Okay, so every time they come out of this trap state and end up in here, they emit a green photon. And because it's very slow, the system, it takes a long time for it to cycle through all of the atoms that were excited and get trapped in. Okay, so even though this is really, really fast, this process is really slow. So the emission of the photons from this intermediate state to the ground state decays very, very slowly. Right? Because it takes a long time for the system to relax. And that's the light that emits from a glow stick. That's why the light in a glow stick lasts for 20 or 30 minutes, because what you're doing is mechanically pumping atoms or molecules or whatever, electrons, into this intermediate state that has a forbidden transition to the ground state that's very, very slow, and therefore any photons that come out of this last for a really long time. It just keeps emitting. Okay? And there's a term for this. This entire concept of using spin-forbidden states to trap population into a lower energy level to tune the photons that come out of the system in the response, and you get a photon of lower energy. Very, very specific term for this called phosphorescence. Right? Like the glow on your, well, think about the glow on your watch, for instance. You ever own those Timex watches that glow in the dark? Right? They don't use radium anymore in those, thank God. They used to be that glow-in-the-dark watches had radium salts painted on the hands, which of course is horribly radioactive and the reason why Marie Curie died in her 40s. Not from watches, just from gross negligence with radioactive materials. So what they instead do is they build dyes, literal dyes. They're organic dyes that are paints that they use, that Timex uses, that uses this process. So they use, instead of in glow-in-the-dark system, you're not using mechanical energy to excite the solution. You use light energy, right? So the photons from your light source during the day pumps your molecules on the face of your clock from the ground state to the excited state. Then as the day progresses, you're continuously pushing more and more molecules into this intermediate state where they get stuck and they emit lower energy or longer wavelength photons that are blue or green or whatever right here. Right? And that's what causes glow-in-the-dark phosphorescence. This only can happen if you have spin-forbidden transitions. It's the only way to slow things down enough of electrons to get them to emit for a long time. All right, so we use this concept of spin-forbidden and spin-orbit coupling to direct advantage to create light sources, long-lasting light sources. Because the fact of the matter is the time, this process right here, right, putting this up in here and then re-emitting back down, right, this happens on the order of a nanosecond for most molecules. sometimes even faster than that. For sodium, this is a 10 nanosecond process, right? So if you had a sodium atom phosphorescence in your lamp, if you're trying to use that, and you want to get sodium, you turn it on, you pump it, and then you turn off your light source that pumps it, and the sodium light dies in 10 nanoseconds. You've killed all of that excitation. So you need to find some way to slow the kinetics down, and so you use this idea that spins can't flip very easily, to trap it into a state which allows it to emit very slowly and for a long period of time. Okay. One more selection rule, really, really simple rule. We have to just combine these together. One more, which is delta J. And this is actually a very good rule in general. This is true for all angular minima. 0 plus or minus 1, right? Think about S can't change, but L can change, so that means J can change by the same amount. But one exception, J equals 0 to J equals 0 is forbidden. So for instance, let's look at helium. Helium's ground state is 1s2. Right? And we calculated last class what the term symbol for this was. It's 1s0. Right? That's a spin configuration. Right? Just 2 electrons in the valence. Right? Octet rule. Fully filled valence. Right? And then let's think about, is there another spin state, for instance, that we could generate that also has the same properties, but L changes? The J is same. So we want something, so we want a transition that where L is 0 but J changes. Or sorry, L changes but J doesn't. So we could, for instance, put this into a state. Right, what about a state that looks like this? 1s in a 2p orbital. And we have this state. All right, so we've taken one electron from S and put it into p. All right, so this, what is the term symbol for this state? Well, it's 1p0. And this is forbidden. Okay, so some of the transitions that, for instance, this is the Lyman transition in hydrogen. You don't get it in helium because it's forbidden, because J isn't changing. All right, so there's some funky intricacies here that doesn't work. Another example of a forbidden transition. So let's just look for one more example. I've got 5 minutes, so let me just do one more classic example. I want to talk about my favorite transition in all of atoms, the sodium D transition. This is the transition of sodium that gives lights on highways that characteristic yellow-brown color. All right, this is the highway yellow light. Okay, and this sodium D transition is a interaction between the ground state, the 2s1/2 state of sodium, and then the 2p states. Right, and there are 2 lines. There's this one, which is called the D1 line, and there's the D2 line. And these are at very, very characteristic wavelengths. This one is at 589.76 nanometers. That's in the yellow. and this one's at 589.16 nanometers. Let me clean that up, sorry. Which is also in the yellow. Okay. So something that might be interesting, right? This looks like the Lyman alpha line. Well, it's not really the Lyman alpha line because we're in the 3 states. These are the, sorry, let me just write that. These are the 3 P's, and this is the 3S. Okay, so this is the transition between the S's and the P's of the 3 state, n equals 3 state. The allowed transitions are D1 and D2. D1 is the 3 to S 1/2 to 3 to P 1/2. Right, this is delta S equals 0, right? The spin isn't changing. J is equal to delta J is equal to 0, and delta L is equal to 1, right? This is allowed, right? J is not changing, spin's not changing, but L is changing, right? This is all good. And D2,
can you just move the page back on?
yeah, sorry. Is that better?
Yeah, so is that 589.6?
The first one's 589.76, and the other one's 589.16.
Okay.
And the D2 line is the 3S state to the 3 to P 3/2 state, which of course is delta S equals 0, but delta J is equal to 1 here. Yeah, delta J is equal to 1, and delta L is equal to 1. Okay, so the D1 state, we're effectively pumping ourselves into a state where the angular minimum hasn't changed at all. Angular minimum is conserved. This is the classic S to P transition without thinking about angular minimum, right? This is what Lyman and those guys would think about. You're just moving from 3S to 3P. That's very common. But there's also this other state where you also can excite the electron, right? We're taking the electron and we're giving it a kick. And now it has an additional unit of angular momentum, and J changes. Right, but there's one transition in this sequence that is forbidden, right? What is that? Well, it's the one between these two. Right, there's also this transition, right? But that's forbidden. So we'll call that D3.
And is that 3 to P 3/2?
Yeah.
Okay.
Sorry, this 3 needs to be bigger. N equals 3. The D3 line, right, that's going to be between the 2 P's. So that's the 3 2P 1/2 to 3 2P 3/2. Here, delta S is equal to 0. Delta J is equal to 1. But delta L is equal to 0. Okay, so this is forbidden. And I just wanted to say what the energy of this is, even if we could see it, right? The energy of this state, the spacing between the levels is 17 wave numbers. Now remember what I said. The spacing between levels goes as n cubed, 1 over n cubed. So as n increases, it gets smaller and smaller, but it gets bigger as z increases. So remember, the spacing between the p levels in the 2 state, 2s, the 2p state, and hydrogen is 0.3 wave numbers. So we've gone up an additional n to n equals 3 in sodium, and we're looking at the same transition, and the spacing between the p states is 17 wave numbers. It's, what is that? Over 60 times the size as it was in hydrogen. Right? So this scales very, very rapidly. And as you get to larger and larger atoms, this spacing gets larger and larger and larger to the point where the level structure that you're used to, right, the Lyman series where you have the little progressions of lines that get closer and closer together, that disappears. It's completely broken because the spin orbit becomes so large that the p orbitals, for instance, will start going below the s orbitals, and the d orbitals and the p orbitals start to mix, right? Everything starts to mix. So when you look at the atomic spectra for big atoms, all hell breaks loose. They don't have the same structures that the hydrogen atom does, because the spin splitting starts to become on the same order of the states themselves, the splitting of the states. And so the spectra get very, very complicated. But the fact of the matter is that we can still label all of the states with these things, right? We can still label every state. We can measure the quantum numbers. They're still good quantum numbers. We can label the states precisely, but calculating their energies becomes more complicated, okay? We'll talk about that on Tuesday. Come back to that from the context of molecules in particular. Okay, have a good one, guys. Now you can finally enjoy your weekend. I don't have office hours tomorrow, I'm sorry, but I'll have them back next week.
Yeah, I was just about to ask. Like, I know I saw your message, but I didn't know if you would still like let people there.
I probably won't have any attention for you.
Yeah,
tomorrow.
that's what I was gonna ask. I'm guessing then you won't have any attention to focus on anything other than installing
Yeah.
the damn thing.
Yeah, so it'll be back to normal, and I'll have more time in 311 next week, so I'll add additional hours.
Well, at least you don't have any more labs left.
That's right.
Thank God I don't want to have to do another iodine lab ever again.
Well, you come do research with me and you can do them for a living.
No way. After this research project I'm doing, I'm never touching it, never want to consider research again.
Thank you.
Until I'm older.
Thank you.